Hello all. In my previous class, I discussed N-type material and its electrical characteristics like charge neutrality of N-type material and conductivity of the N-type material. And also I discussed calculation of the Fermi level in a N-type material. Right? Now in this class, I will start with the effect of doping on energy band diagram. Right. Effect of doping on energy band diagram actually, right? See, in case of N-type material, so which type of impurities are added actually? Pentavalent, right? See, when the pentavalent impurity is added, or it is also called as what actually donor impurity, right? Okay. So when pentavalent impurity is added to the pure form of semiconductor actually, what happened to the energy band diagram? See here, a new energy level is created. When we add the pentavalent impurity to the energy band diagram actually, a new energy level is created, okay, below the conduction band. That new energy level is called as what actually? Donor energy level, right? Donor energy level. Right. Now, here when a small amount of energy is given, what happen actually? So these electrons means electrons in the donor energy level can move from donor energy level to conduction band. So this is called as what actually? Impurity ionization. Impurity ionization. Similarly, actually a few electrons are moving from valency band to conduction band, right? So when the electrons are moving from valency band to conduction band, then it is called as what actually? Band to band transition actually. Band to band transition. See, in an intrinsic semiconductor, the conductivity is due to only one type of mechanism, that is due to band to band transition. But whereas in extrinsic semiconductor, that may be an N-type or a P-type. Okay, the conductivity is due to two types of mechanism. One is band to band transition, another one is impurity ionization actually. See, this impurity ionization because of what? Doping process. Doping process. So this is the effect of doping on energy band diagram actually, right? Copy the energy band diagram first. Right. Write in the notes. When the pentavalent impurity is added to the intrinsic semiconductor, then a new energy level is created. A new energy level is created below the conduction band. Below the conduction band. That new energy level is called as donor energy level. Donor energy level. In bracket ED. Underline donor energy level. Right. Next point. When the small amount of energy is given to the semiconductor, when a small amount of energy is given to a semiconductor, then electrons are moving from donor energy level to conduction band. donor energy level to conduction band. Then it is called as impurity ionization. Impurity ionization. Yeah, underline impurity ionization. Underline impurity ionization. Yeah. Next point. Similarly, few electrons are moving from valence band to conduction band. Similarly, few electrons are moving from valence band to conduction band. Then it is called as band to band transition. Band to band transition. Yeah, underline band to band transition. Right. Next. Yeah, next, see, when the n-type semiconductor is lightly doped, what happens? See, when the n-type semiconductor is lightly doped, what happened to the energy band diagrams here? What happened? Donor energy level is formed. But you know that donor energy level is a single line because of lightly doping. See, similarly, when the n-type semiconductor is heavily doped, that means you can increase the doping concentration more, right? Heavily doped, then what happen actually? See here, the energy gap is decreases because of this heavily doping. Why energy gap is decreases actually? Because interaction between the atoms is increases. Interaction between the atoms increases. Due to which, right? So multi-energy levels are formed. Due to which energy gap is decreased. See here, in case of lightly doped, actually energy level is a single line. But in case of heavily doped, actually multi-energy levels are formed because of heavily doping. Due to which energy gap is decreased. Decreased by an amount of how much? By an amount of delta Eg. Right. So this is for lightly doping. Figure 1. And figure 2 is for heavily doping. Right. Okay. See here, because of heavily doping is what happened to the concentration. See all of you, how to calculate the concentration. See for any semiconductor, okay, what will be the relation between electron concentration and hole concentration actually here? Np equal to A naught into T cube e power minus Eg by kT, right? So this is for any semiconductor. Any semiconductor means it may be intrinsic or extrinsic, okay? Similarly for heavily doped semiconductor, means that may be n-type or p-type. What happened actually? So what happened for heavily doped semiconductor actually? Energy gap is decreases by an amount of how much? Delta Eg, right? Now what it is actually, this is Nn into Pn equal to A naught into T cube e power Ag minus delta Ag by kT, right? Now A naught into T cube e power minus Eg by kT into delta e power Eg by kT. Actually, what is the value of A naught into T cube e power minus Eg by kT? Actually, this is simply Ni square. Now Nn into Pn is equal to Ni square into e power delta Eg by kT, right? Now see this equation actually here, means what is the conclusion here? See, for heavily doped semiconductor, okay, the mass action law is does not valid. What is mass action law actually? Okay, the product of electron concentration and hole concentration is equal to square of intrinsic concentration, that is mass action law. But in case of heavily doped semiconductor, actually this NP is not equal to Ni square, not equal to Ni square, right? Copy, write in the notes first. When the semiconductor is lightly doped, when the semiconductor is lightly doped, then the donor energy level is a single line. The donor energy level is a single line. Yeah, next point. When the semiconductor is heavily doped, when the semiconductor is heavily doped, then the donor energy level can be split into multiple energy levels. Multiple energy levels, due to which energy gap is decreases. Due to which energy gap is decreases by an amount of delta EC. Energy gap is decreases by an amount of delta EC. Right? Underline by an amount of delta EC. Right? And copy the derivation. First copy the diagrams, after that copy the derivation actually. Right, write down. That is, for heavily doped semiconductor, the mass action law does not valid. Mass action law does not valid. Right. Very, very, very important point. Underline that point. Right. Next. Write down a question. In classroom workbook, question number 3. Question number 3 in classroom workbook. A pure silicon sample has Ni equal to 1.5 into 10 power 10. Ni equal to 1.5 into 10 power 10 at room temperature. And it is heavily doped with phosphorus, due to which energy gap is decreases by an amount of 0.06 electron volt. 0.06 electron volt. Find free electron and hole concentration. When net impurity concentration is 10 power 19 per centimeter cube. 10 power 19 per centimeter cube. Right. Once again, all of you read the question once actually here. They given what actually a pure silicon sample, right? They given a pure silicon sample. It has intrinsic concentration, how much? 1.5 into 10 power 10. And it is heavily doped with what actually? Phosphorus. Heavily doped means this become N+. Right? Due to which, what happened to the energy gap actually? Energy gap is decreases by an amount of how much? 0.06. That means delta is equal to 0.06 electron volt. Okay. Also, what we want to calculate here? Free electron and hole concentration when net impurity concentration is 10 power 19. That means the given Nd donor concentration is how much? 10 power 19 per centimeter cube. Yeah, this is the given data. Here, how to calculate free electron concentration and hole concentrations actually, right? We have two formulas, right? For calculation of free electron concentration and hole concentration, actually we have two formulas. One is exact formula, another one is approximate formula, right? So for this example, so which formula is suitable, right? See all of you. So here Ni is 10 power 10, Nd is 10 power 19. That means clearly here Nd is far greater than Ni. If Nd is far greater than Ni means, so we can go for approximation. That is, Nn is approximately equal to Nd, so which is equal to how much? 10 power 19 per centimeter cube. Right? Next, Pn actually, hole concentration. The hole concentration Pn is equal to Ni square by Nd. Is it correct? Actually, what is this? Pn is equal to Ni square by Nd. Actually, this is the mass action law. But here, what is our semiconductor? Heavily doped. Just now I told, for heavily doped semiconductor, the mass action law does not valid. Then how to calculate this hole concentration actually? Okay, we can use this expression actually. This expression. What is that? See, for heavily doped semiconductor. For heavily doped semiconductor. So, Np equal to Ni square into e power delta Eg by Kd. Now from this, what about the hole concentration? Hole concentration is equal to Ni square by N into e power delta Eg by Kd. What about Ni here? Actually, Ni is nothing but 1.5 into 10 power 10 whole square by N. N is nothing but how much? 10 power 19 into e power 0.06 by 0.026. So, which is equal to 226.1 per centimeter cube. Right. So, this is the hole concentration and this is the electron concentration. Copy? Right. Next topic. Another classification of extrinsic semiconductor, that is P-type. N-type is completed. The next topic is P-type semiconductor. So now, see, this P-type semiconductor is formed. This P-type semiconductor is formed actually by adding trivalent impurities. Trivalent impurities are nothing but third group elements to the pure form of semiconductor like silicon or germanium. See, what are the third group elements actually? The third group elements are nothing but boron, aluminium, gallium, indium, and thallium, right? These are the third group elements actually. See here, for making of p-type semiconductor in any electronic device, that may be NPN or PNP actually, generally we prefer boron only, because the boron has greater affinity actually. Write down. P-type semiconductor is formed. P-type semiconductor is formed by adding trivalent impurities to the pure form of semiconductor like silicon or germanium. Example, boron, aluminium, gallium, indium, thallium. Right. Next point, note. See, for making of p-type semiconductor, boron is preferred because it offers greater affinity. Right. Now copy this figure. P-type semiconductor. Right. Yeah. So now, see, this p-type semiconductor is formed by adding trivalent impurities. Okay. Then this trivalent impurity can replace the semiconductor atom, due to which 3 valence electrons are involving in covalent bond formation, and the fourth one does not involve any covalent bond formation. Right? Due to which, what about the hole concentration actually? The hole concentration is increases, and also recombination rate is increases. Recombination rate increases. That means the few holes recombine with the few electrons. Then what about the electron concentration actually? The electron concentration is decreases. That means for better understanding actually, here. See, I am considering the pure semiconductor. What is the condition for the pure semiconductor? N equal to P. Right? So we are adding which kind of impurities? Trivalent impurities actually. Okay, due to this trivalent impurities, which concentration is increased? Hole concentration is increased because only three are involving in covalent bond formation. The fourth one does not involve any covalent bond formation, right? Okay, due to which hole concentration is increases. See, when we add this trivalent impurity to the pure form of semiconductor, what happen? You know, the few holes are recombined with the electrons present in the intrinsic semiconductor, right? So due to which what happen actually, electron concentration is increased. See, one side the whole concentration is increased because of adding of trivalent impurities. Other side the electron concentration is decreased due to recombination. That means in a p-type semiconductor, so which one is the majority? The holes will be the majority and the electrons will be the minority, right? And one more point actually, this added trivalent impurity, okay, can accept the electron from the nearby atom because this is vacant, right? So it can accept the electron from the nearby atom, so that it is also called as what actually? Acceptor impurity. See, where n type, that is called as donor impurity. Here this trivalent impurity is called as what actually? Acceptor impurity, right? Huh. Write in the notes. Write in the notes. The added trivalent impurity, the added trivalent impurity can replace the added trivalent impurity can replace the semiconductor atom, can replace the semiconductor atom, due to which three valency electrons are involving in covalent bond formation, and fourth one does not involve any covalent bond formation. Fourth one does not involve any covalent bond formation, due to which hole concentration is increases. Hole concentration is increases. Yeah, underline hole concentration is increases, and also recombination rate increases. Recombination rate increases. That is, few holes recombine with few electrons. Few holes recombine with few electrons. Right. As a result, next point, as a result, free electron concentration is decreases. Free electron concentration is decreases. Yeah, underline free electron concentration is decreases. Right. Next point. Hence, in p-type semiconductor, the majority charge carriers are holes. Majority charge carriers are holes, and the minority charge carriers are free electrons. Minority charge carriers are free electrons. Yeah, underline majority as holes and minority are free electrons. Right. Next point. The added trivalent impurity can accept the electron from the nearby atom. Can accept the electron from the nearby atom, so that it is also called as acceptor impurity. It is also called as acceptor impurity. Yeah, underline acceptor impurity. Next topic, charge neutrality or electrical neutrality of a p-type semiconductor. Right. See, what is the charge neutrality or electrical neutrality of a p-type semiconductor actually? I already told. See, charge neutrality or electrical neutrality means the net amount of negative charge equal to net amount of the positive charge. See, in case of p-type semiconductor also, the net amount of negative charge equal to net amount of positive charge. See here, net amount of negative charge is equal to net amount of positive charge. Right. See, tell me, what is the net amount of negative charge in p-type semiconductor actually? Electron concentration in p-type semiconductor. What is the net amount of positive charge in p-type semiconductor actually? The whole concentration in p-type semiconductor. Actually, what is this? N equal to P. N equal to P means it is an intrinsic sample. But here what we are talking p-type semiconductor, right? In p-type actually, okay, we can accept the electron from the nearby atom, right? We can accept the electron from the nearby atom means it can get positive charge or negative charge? Negative charge. That means we can add the acceptors on P side or N side? N side to balance this equation, right? So this is the charge neutrality equation in case of the p-type semiconductor. Already I discussed the charge neutrality equation in n-type semiconductor. Similarly same in p-type semiconductor also, right? Now it can be considered as equation 1. So here how to calculate this whole concentration and electron concentration in a p-type semiconductor, right? By using mass action law. By using mass action law, right? So what is mass action law? Mass action law is nothing but the product of electron concentration and the whole concentration is equal to square of intrinsic concentration, right? Now from this, what about NP here? NP is equal to Ni square by Pp. This is equation 2. Substitute equation 2 in equation 1, right? Now after substitution, what is this equation? This is Ni square, equation 1, Ni square by Pp plus Na is equal to Pp. Now it is equal to Pp square minus Na into Pp minus Ni square, which is equal to 0, right? Now how to resolve this equation actually here? This Pp equal to minus b plus or minus root of b square minus 4ac, right? See here. So this is minus of minus means plus Na plus or minus root of b square, that is Na square minus 4ac, that is 4 into a is 1 and c is minus Na square, it becomes plus Ni square by 2a, right? A is 1. But here the concentration must be in positive, so consider only the positive value. This is the equation for calculation of the whole concentration. Now how to calculate electron concentration actually in case of p-type? Use this mass action law, that is Ni square by P. Actually these two equations are called as what actually? Exact equations. Exact equations. Right? Next I can also go for approximation actually. In case of approximation, okay, we can consider one condition actually, that is Na is far greater than Ni. If Na is far greater than Ni, then what should be the whole concentration actually? The whole concentration should be equal to Na square plus under root of Na square by 2, so which is equal to Na. And what should be the electron concentration actually? That is Ni square by Pp. But what about the Pp value here? Na. These two are approximate equations actually. Right. Copy. First write down. Actually. The p-type semiconductor is said to be. The p-type semiconductor is said to be electrically neutral or charge neutral. Electrically neutral or charge neutral because net amount of, write down like this, net amount of negative charge equal to net amount of positive charge. Net amount of positive charge. Right. Copy? Copy the derivation. Yeah. Next topic. Calculation of conductivity of a p-type semiconductor. In bracket sigma p. Calculation of conductivity of a p-type semiconductor, sigma p, right? See how to calculate the conductivity for a p-type semiconductor. First I can define for any semiconductor. See for any semiconductor what is the conductivity equation? For any semiconductor means that may be intrinsic or extrinsic. What is the conductivity equation actually? N into E into mu n plus P into E into mu p. This is the equation for conductivity for any semiconductor, right? Now I can define for p-type semiconductor. See for p-type semiconductor, what is the conductivity equation? Actually sigma p equal to this n become np into E into mu n plus pp into E into mu p, right? This is the exact formula for calculation of conductivity for p-type semiconductor. See, I can also go for approximation actually. In approximation actually here I am considering one condition. What is that condition? The hole concentration is far greater than electron concentration, right? Because in p-type semiconductor the majority are holes and the minority are electrons, right? Then what should be the conductivity actually? Sigma p is approximately equal to pp into E into mu p. Now what is pp here actually? The pp is nothing but okay Na into E into mu p, right? So this is the approximate formula, right? This is the calculation of conductivity of a p-type semiconductor. Copy? Right. Next topic. Calculation of Fermi level of a p-type semiconductor. Calculation of Fermi level of a p-type semiconductor, right? That is in bracket EFP. Right. How to calculate the Fermi level of a p-type semiconductor? See, first I can define for any semiconductor. See, for any semiconductor, what will be the hole concentration actually? P equal to NV into E power minus of EF minus EV by KT. So this is equation 1. This is the equation for calculation of the hole concentration for any semiconductor, right? Now I can define for p-type semiconductor. See, for p-type semiconductor, what will be the hole concentration? Actually, the hole concentration is nothing but acceptor concentration, and EF equal to what actually? EFP, right? This is equation 2. See, from equation 1 and equation 2, from equation 1 and equation 2, the hole concentration is nothing but what actually? Hole concentration is nothing but acceptor concentration, which is equal to NV into E power. This EF become actually what? EFP minus EV by KT, right? Now from this, NV by NA is equal to E power EFP minus EV by KT. Take logarithmic on both sides actually. That is EFP minus EV by KT is equal to ln of NV by NA. Now EFP minus EV is equal to KT into ln of NV by NA. Now EFP equal to EV plus KT of ln of NV by NA. So this is the equation for what actually? Calculation of Fermi level of a p-type semiconductor. Right? Now from this equation, what is the conclusion? See, for a p-type semiconductor, so where is the Fermi level actually? This is the valency band, right? This is the conduction band. EFP equal to EV plus. EV plus means I think it is lies above. Plus KT into ln of NV by NA. Actually this value is very, very small value. That means in case of p-type semiconductor, actually the Fermi level lies above the valency band. Right? Copy? Right. Right on? For p-type semiconductor, the Fermi level lies above the valency band. The Fermi level lies above the valency band. Next note, very, very, very important note. Right. So all of you, see, in case of p-type semiconductor, if NV is greater than NA, see, if NV is greater than NA, then what about the EFP minus EV actually? EFP minus EV is positive, right? If NV is greater than NA means I think this value is logarithmic value is positive, then EFP minus EV equal to what actually? Positive. That means EFP minus EV equal to positive means what is the conclusion? The Fermi level lies above the valency band, right? Similarly, if NV is less than NA, what about the EFP minus EV actually? Negative, right? That means where is the Fermi level actually? The Fermi level lies within a valency band. Okay. Next, if NV equal to NA, then what about the EFP minus EV actually? 0. EFP minus EV equal to 0 means where is the Fermi level actually? The Fermi level is coincide with the valency band. Right? Right on? Note. First point, if NV is greater than NA, then EFP minus EV equal to positive. That is, the Fermi level lies above the valency band. Next, second point. If NV is less than NA, then EFP minus EV equal to negative. That is, the Fermi level lies within a valency band. Third point, if NV equal to NA, then EFP minus EV equal to 0. That is, the Fermi level coincide with the valency band. Next, right? Next one, observation. Next point, observation, right? See, what is an observation actually here? See, the p-type semiconductor enrich. The Fermi level lies within a valency band or coincide with the valency band Such a semiconductor is called as what actually? Degenerative or heavily doped p-type semiconductor. What? Degenerative or heavily doped p-type semiconductor. Similarly, the Fermi level lies within a valency band, above the valency band. Above the valency band, such a semiconductor is called as what actually? Lightly doped or non-degenerative p-type semiconductor. Right? Right on? This point also. Observation. The p-type semiconductor in which the Fermi level lies within a valency band or coincide with the valency band. Such a semiconductor is called as degenerative or heavily doped p-type semiconductor. Heavily doped p-type semiconductor. Yeah, underline heavily doped degenerative. Right. Next point. The Fermi level lies above the valency band. Such a semiconductor is called as lightly doped or non-degenerative p-type semiconductor. Right? Underline lightly doped, non-degeneratively doped. Yeah. Thank you. And to be continued in next lecture.